course has been largely about pure mathematics without much in the way of applications. But to finish the unit, I would like to, in a pair of lectures, talk about a place where we could apply these ideas that we've been learning about sequences of numbers and recursion. And what I have in mind is models of population growth. So what we're doing here is a little bit of the beginnings of a subject called mathematical biology. And this is a big deal at Ohio State. In the United States, there is one NSF-funded research institute in mathematical biology, and it's right here in Jennings Hall on the campus of Ohio State. It's the Mathematical Biosciences Institute. Now, just to give you some idea what kind of things go on there, I've chosen to show you the titles of a couple of upcoming talks. One of them, as you can see, has to do with genetics. So somehow genetics, the study of genetics, can involve an awful lot of mathematics. Statistics, in part, but also rather high-powered and esoteric kinds of mathematics. Quite surprising sometimes. Another subject a little bit closer to what we're talking about here today is the other talk that's shown there. It's something about population management, and we will be looking at models of population growth. Now, naturally, I don't expect that you understand the titles of these talks. I don't understand them myself. But just to give you some idea what is the general subject area and to let you know that it's actually going on right here at our university. Now, as I've said, the particular topic I want to look at is models of population growth. So we're thinking about the population of some kind of organism. It could be a microorganism, and you could be studying it in your laboratory, in your test tubes, looking at it through microscopes, perhaps. Or it could be some kind of wild population. Maybe you travel over to Africa and you study whatever there. You study zebras, or you study lions. Okay. Now, among the things that you're doing when you do this study is simple counting or measuring. You just want to know, how many organisms do I have? So we're wondering, can we model that in any way? Now, if you want to create a mathematical model of population growth, right at the very beginning, there's a basic choice that you need to make between two types of models. They're called continuous growth models and discrete growth models. And here's the difference. In a continuous growth model, the assumption is that the population is changing at every moment. In a discrete growth model, we assume that the population changes only at certain moments, separated by intervals of time. Now, you might be doing that because you think that's really the way the situation is, or maybe because this is the way that you measure it. So even if you think the population is changing at every moment, maybe you only go and count it or measure it once a day or once a year. So as far as you're concerned, you don't have any evidence for what's happening in between times. So as far as you're concerned, it's as if the population were changing only at these particular moments. Now, if you choose to go with a continuous growth model, then the kind of picture you might be drawing to describe your model is what's shown on the left. So there's some initial population. That's right where that purple curve starts on the vertical axis. There's some initial population. Here it looks rather small. And then as you move to the right and follow that curve, you can see how the population is rising or declining in time. In this particular example, we're seeing growth up to a certain point at time, maybe time 9 or 10, and then there's decline after that. In the discrete growth model, if you want to draw a picture, well, this time, rather than drawing a curve, which is what we drew over on the left, you would simply draw discrete dots, okay, dots with space between them, because you're assuming that you don't know anything about the population at intermediate times. You know just what's happening at time 0, say, at time 1, at time 2, and so on. Now, if you're studying this subject, how do you choose your model? Well, one way that you choose your model is in trying to capture the features of whatever you're studying as well as you can. So that's one consideration. But another consideration is, well, what is it you're going to have to do when you're studying your model? In other words, what kind of mathematics will it involve? Well, in the case of continuous growth models, I can give you a one-word answer. The mathematical tool that you'll need to use in studying these models is calculus. This is what the subject of calculus is about. Calculus is about studying things that are changing at every moment, things that are changing continuously. On the other hand, if you're going to study discrete growth models, then you're going to use the kind of tools that we've been studying in this unit. You're going to study sequences and recursion. Well, for us then, I guess the choice is sort of obvious. I'm not assuming that anyone in this course knows any calculus at all, so we can't do anything further with continuous growth models. And for the rest of our study, we'll be looking at certain discrete growth models. Now, in the discrete growth models that we're going to study, we're working with a sequence. There's some initial population value, which we'll denote by p sub 0. You might notice one small thing I'm doing here that's a change from what we did earlier in the unit. I'm going to call the initial value of the sequence p0 rather than p1. p0 meaning the population at the beginning of time, at time 0. It's sort of natural in this context to be thinking about calling it p0 rather than p1. Now, in all our models, there will be some sort of a transition rule. The transition rule will tell you, if you know the initial population p0, how to calculate p1, and then using the same transition rule, how to calculate from p1 the value of p2. And then applying the transition rule again to p2, you get p3, and so on. So there's some transition rule that will generate the sequence by going from p0 to p1 to p2, and so on. You realize we've talked about this already in slightly different language when we were using our recursive formulas. Now, we're going to learn about 3 discrete growth models. These are not the only types that are possible. In some sense, these are the simplest ones that one might write down at the very beginning of studying a population sequence. The 3 that we're going to learn are called linear growth models, exponential growth models, and logistic growth models. And we will study them in this order. In fact, the first one is the simplest, and then the others are increasingly more sophisticated. Now, in the remainder of this lecture, we'll look at the first 2 because that's rather brief, and then we'll look at the logistic growth model all by itself in the last lecture of the unit. That is to say, the next lecture after this one. So, first of the 3 types is linear growth models. And here we begin with the assumption that during each interval, the population grows by the same fixed amount, d. That is to say, our transition rule says that population at time n is the population at time n minus 1 plus the number d, whatever it may be. Now, as soon as I say that, you say, oh, well, we've studied this already. You're telling me that we're looking at an arithmetic sequence. Yes, indeed. So linear growth models are those in which the population sequence is an arithmetic sequence. That is to say, a sequence obtained by always adding the same fixed amount. Now, one thing that I never mentioned before when we studied arithmetic sequences is that you can actually write down an explicit formula in these cases. That is to say, a formula that is not recursive. Just think about it. You start with a population p0, and to get to p1, you add d. Then to get p2, you add it again. Then to get p3, you add it again. So all you do to get terms in this sequence is to add on d as many times as you need to get to the value you're interested in. If you want to get to the population at time n, then you start with the initial population P0 and you add on the number D n times. So we have this explicit formula, Pn is P0 plus Nd. Now here I'm showing you what you'll get if you plot the population values in a linear growth model. That is to say, if you plot an arithmetic sequence, and what you will get is points that seem to lie on a line. And that's why we call it a linear growth model. Before we leave it, let's talk about its limitations. A linear growth model assumes, for example, that if 100 rabbits can produce 10 baby rabbits in a month, then 500 rabbits can also produce 10 babies. You see, it assumes no matter how large the population is, that it'll just produce the same number of babies each time. And you might say, well, that's not very realistic. You'd expect if you have more rabbits, they could produce more babies, right? You might think if 100 rabbits can produce 10 babies, maybe 500 rabbits could produce 50 babies. And that's the kind of thinking that leads us to think about the next sort of model, which is called the exponential growth model. Here we assume that during each interval, the population grows not by the same fixed amount, but by the same fraction of itself. And if you've made that assumption, then you'll be led to this other transition rule, in other words, this other recursive formula that says that the population at any time is what you get from the population at the previous time multiplied by a number, and of course we're going to call that number R. That's what we called it before, because the population sequence, indeed, is a geometric sequence. Now, we can again write an explicit formula, because note that to get from the initial population to the population at time n, what we have done is to multiply by this number R over and over again, repeatedly, right? We've done it n times. And when you multiply by something n times, it's as if you've multiplied by that number raised to the nth power. So the explicit formula is Pn equals P0 times R to the n. Here I'm showing you plots of exponential growth models. And I'm showing you two examples because the behavior that you will get in an exponential growth model actually depends on the nature of the number R that you're using. And the important distinction is between cases where R is greater than 1 and cases where R is between 0 and 1. Of course, you wouldn't think of using a negative number. That would lead to some crazy things when you're thinking about populations. You can't have a negative population, so don't allow R to be negative. So the basic distinction is between R greater than 1 or R less than 1. And the difference between them is when R is greater than 1, then the population is being multiplied by something that makes it larger each time, whereas if you multiply by something less than 1, it makes it smaller. So when R is greater than 1, indeed, it looks like growth, and the phrase exponential growth seems to fit it rather well. On the other hand, if R is less than 1, then you get something that we might better call exponential decay. You see the population is declining. Now, these growth models also have a limitation. One limitation is that there's only two sorts of behaviors that they can have, depending on whether R is greater than 1 or R is less than 1. Namely, either the population dies out. It's always decreasing and it slowly approaches the value 0. As we say in mathematics, it approaches the value 0 asymptotically. The other possibility, and this is when R is greater than 1, the population grows forever and there's no bound on it. Okay, you might not realize it from the picture on the left, but in fact, in this population model, that curve will go up to an arbitrary height. There is no upper bound for that population. Now, although the first behavior, the population dying out, might seem pretty plausible, the second is clearly impossible. So the exponential growth model isn't good in all situations. It's really good in situations where the population size is relatively small and there's little competition for whatever resources the population needs. So as a nice example of that, in the early days of European exploration and colonization, these sailing ships would land on remote islands, and often they would have rats on board. Well, when they landed, the rats would jump off, go onto the island, and they found themselves in paradise. They found everything that a rat could possibly want, and the only limitation on their growth was how fast they could reproduce. So the population of these rats exploded, and in fact, it probably was fit very well by an exponential model. But a real-world population outside of the situation that I've just talked about is constrained by its habitat. There's competition for food. There's competition to avoid predators. There's competition for mates. There's an awful lot that constrains this growth, and in particular, it doesn't seem at all plausible that the population could grow forever without bound.